So welcome back. We've covered most of the topics we need to cover in this course now, but we have one more topic remaining that's important for the description of the standard model of elementary particle interactions. And that's a topic known as spontaneous symmetry breaking. So this is a little bit different from the things we've seen so far. So far we've been building theories in terms of fields, and we've been building fields in terms of symmetries. Now we've got all the fields that we need to build the standard model, but there's still some behaviors of these field theories that we need to understand before we can really explain all the pieces of the standard model. And so one behavior that we need to cover is something called spontaneous symmetry breaking. Okay, so I'll start by giving a very, very simple classical example of spontaneous symmetry breaking. And then as the lecture progresses, we'll generalize this example further and further and further to apply to more and more complicated examples till we come to the field theories that make up the standard model. So the first example of this phenomenon known as spontaneous symmetry breaking is a classical particle in a double well. This is a not quite example, but it's one that'll get you into on the quantum side, it's not quite an example of spontaneous symmetry breaking, but it'll get us in the mood for the actual examples. So here the classical Hamiltonian for this system, let's take it to be a single non-relativistic classical particle and some potential, and this potential, let it be this double well potential like this. So this system has a Z2 symmetry if we replace x by minus x, we get the same dynamics. But, the ground state of this system doesn't respect the symmetry. So the ground state of this classical system, this particle, is either x minus or x plus. The particle is either here or there. So there's no one unique ground state for the system. Even though the system has this symmetry, each ground state breaks that symmetry, so you have to choose which local minima you're going to go into, and then once you've done that, you've broken this Z2 symmetry of the model. And, well, that's it. That's all there is to this example, right? So the symmetry isn't lost. I mean, the Hamiltonian still has that symmetry. And where has the symmetry gone? Well, it's created this degeneracy here. Each ground state is not symmetric under Z2, but the ground state manifold is. In this case, manifold's maybe not the right word because there's only two ground states and they're not continuously connected. Now, that's a simple example as I can think of, pretty much, for this symmetry breaking phenomenon. But it's a not quite example, as we'll see. So I'm going to now discuss the quantum version of this and how the quantum version isn't really exhibiting this example, this phenomena of spontaneous symmetry breaking. So on the quantum side, and then as we go along and consider examples that are more appropriate for field theory, we'll see how field theory forces also the quantum side to break symmetries. At the moment, the quantum side doesn't. Now assume you've met the double well in non-relativistic quantum mechanics before. So you know, I hope, the basics of its eigenstate structure. So we know that the ground state wave function for the double well is, well, what does it look like? Well, it looks like the ground state of this harmonic oscillator. You think of this well here as being basically a harmonic oscillator, and the ground state wave function looks like an equal superposition of a Gaussian here and here, because a Gaussian is the ground state of a harmonic oscillator. So this only makes sense when this approximation only really works when the barrier is quite high. When the barrier is too low, then this approximation doesn't quite work anymore. So that's the ground state, and it's clearly symmetric under Z2, right? If I exchange x with minus x, I get the same state again. And psi 1x, the first excited state, that has that characteristic form, is separated by a small gap. The gap's related to the barrier depth here, and so on. So this is a case where the classical side exhibits symmetry breaking. There are two ground states which are degenerate, each of which break the symmetry. But on the quantum side, well, not really, right? Because the ground state is actually symmetric under Z2. It doesn't break that symmetry at all. So that's but this is the building block, this example, for more complicated examples. Now I'm going to give a statistical physics example. So the statistical physics example is the Ising model of ferromagnetism. So this is the way to describe the dynamics of magnets, of ferromagnets, for reasonably low temperatures. It's a pretty good model for how a hard drive behaves in response to a magnetic field. So the Hamiltonian, this is a purely classical model. So what the Ising model pertains to a grid of spins that can either point up or down. And it's a classical model, so the spins point either up or down. And so the value, the Hamiltonian for this model is a sum of terms which penalize you if the spins are anti-aligned and don't penalize you if they are aligned. So the spins take their values in plus minus 1, like this. And so if the spins are pointing in the same direction, like plus 1 and plus 1, then that gives you -1 to the energy here. And if they point in opposite directions, then it gives you a positive contribution to the energy there. So this Hamiltonian likes everything to point in the same direction. So there's two obvious ground states. There's the all up ground state, and there's the all down ground state. This model also has Z2 symmetry. But this time acting on the spins. And where does the symmetry breaking come into? Well, if you consider the thermal state of this system, then we have two different regimes depending on the temperature. So let's look at the Gibbs state for this Hamiltonian. And if you look at that Gibbs state, then you can see that it is exactly Z2 symmetric. Because H is Z2 symmetric, H appears here. So this mixed state here, describing the state of the system, for all temperatures is Z2 symmetric. No symmetry is broken by this density operator here. But small fluctuations will lead to a breaking of symmetry in this model, depending on the temperature. So there is a critical temperature . So as beta tends to infinity, as you go to zero temperature, the system will become ordered. And what does that mean? That means that this statistical ensemble here of all the states of the system will start to look like, with probability 1/2 minus epsilon, it's the all up state. And with probability 1/2 minus epsilon, it's the all down state. And plus some corrections, some small corrections. And then here comes an additional physical process that I didn't need to introduce in the first example. The fluctuations So the symmetry breaking occurs when there are small magnetic field fluctuations. So there's always small fluctuations in the magnetic field, I mean, even due to the quantum effects. And before the fluctuations, in a perfectly symmetric world with no external magnetic field fluctuations or perturbations, the thermal state of the system really is completely Z2 symmetric. It's got equal probability for having the all up state and equal probability for having the all down state. But the second there's a little bit of external magnetic field anywhere, then that will prefer this one or this one, depending on where the magnetic field is pointing. It could be a magnetic field on just one spin. It's all it takes, just a little fluctuation, magnetic field on one spin, and then that drives the system either into this state or that state. But see that the word fluctuation was really crucial there, to select out one of these states that the system will find itself in. So this is, if you think of the hard drive in, well, maybe no one has a hard drive anymore, but if you did, then you would imagine that you're below this critical temperature. You don't want to be above it, that's bad. And you want to store some information in the hard drive. So, well, you lower the temperature, and all you know, as you've lowered the temperature, is that the system is with 50% probability in this state and within 50% probability in this state, and some corrections. But then you know there's going to be a magnetic field fluctuation which will select out one of these two states, and then you know that the hard drive is definitely in one of these two states here after a perturbation. You can read that out, and then you can start to modify it to store information. That's an example. Oh yeah, and above this critical temperature, the system is disordered. So it's the magnet is just a bunch of independently fluctuating spins, and that also has Z2 symmetry, but a magnetic field doesn't break that symmetry. A small fluctuation won't break that symmetry in the same way that it did here. It'll slightly magnetize the state, but it won't select one of two possible configurations. That's the second example of this thing called symmetry breaking. There's another example. So far we've been looking at systems with a discrete symmetry. The system is invariant under some discrete symmetry group. But there are also systems that are symmetric under continuous groups of symmetries. And they're the ones we've been spending a lot of time with in relativistic quantum field theory. Our group of symmetries is variously the Poincare group, the rotation group, or maybe the conformal group. There's always some group of symmetries. And we may wonder if it's possible to cook up systems which are symmetric under some continuous group of symmetries, and then they prefer, the lowest energy states prefer to break those continuous symmetries. Well, there's a very easy classical model that does that, and it's the inverted pendulum. So if you take a pendulum, this is a pendulum, it's actually not that bad. You pin it there to some kind of fixed reference point, and you take this pendulum, then this is not the lowest energy configuration for this pendulum. A pendulum on a surface. It's important that there's this surface here. So the system comprising of a flat surface and a pendulum fixed to this point on this flat surface, that's invariant under rotation. So you can rotate it, you still get the same Hamiltonian. And it's got a metastable state here, right? It's standing up. But its ground state, what does it do? Well, it falls down, hits the table. Now it's in its lowest energy configuration. And depending on the fluctuation that did that, it will point in a different direction. So that's actually a very simple example of a breaking of a continuous symmetry. Yeah, but I won't cover that just yet. First, I'll cover a field theory with a Z2 symmetry breaking first. let's cover the canonical, simplest first example of symmetry breaking in a field theory. It's all classical still. All right, that's a classical field theory Lagrange density right there. But it's different from the ones you're used to, because this parameter here is negative relative to the usual case. You know, usually this is minus a half the mass squared times by phi squared. So notice that this field theory here has a minus sign in front of this positive parameter there. So it's perfectly sensible, perfectly allowed to write down such Lagrange densities, but you can no longer interpret that parameter there as a mass. But remember, they're just parameters, right? They're just coupling constants. We're not meant to operationally interpret these numbers. You can only operationally interpret quantities you can measure. And quantities you can measure are some weird functions of these parameters, which are just free parameters there for you to fit with the experiment. Now the Hamiltonian for this field, if you go through and do the Legendre transformation, blah, 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 then the classical Hamiltonian for this field has a certain form, and it's one that's, I hope, familiar to you by now. There's some momentum density. There's some shearing density. And then we have this negative mass type term. I call it type because it's not a mass. And then we have the nonlinearity right there. Now, what we want to look at is, well, let's ask the question, what's the field configuration that has the smallest energy? This is all classical. So we just have to find a function phi that minimizes this functional here. So firstly, you know that d phi dt will be 0 for the lowest energy configuration. So this term here is obviously not going to play a role in determining the field configuration that minimizes the energy. Secondly, this is positive. So if you can make that 0, then you know you've got a lower energy. So the classical configuration which minimizes this Hamiltonian will have 0 gradient like this. And then you're just left with this term here, v of phi. And the configuration that minimizes this energy of this Hamiltonian here is one that minimizes that function there. So we can work that out. The minima will occur when the derivative of v with respect to phi is 0. This is mu squared phi minus plus lambda on 6 phi cubed. So we have a condition for our field, our classical field, to be a minimum of this Hamilton functional. And it's this condition here. And this has 3 solutions. It's a cubic equation. let's find those solutions. So factorize this equation here. All right. Yo, a question?
I couldn't really follow your argument why the gradient has to be 0. How do I know that I wouldn't have to make some kind of trade-off that the gradient is a bit above 0 so that I can get the other terms even?
Okay, it's a good question. The question is, how do we really know that the gradient is 0? Couldn't there be some kind of trade-off where we can take the gradient to be slightly above 0 and then get a lower energy by paying less here? Well, there's a kind of simple answer to that. Suppose the gradient is not 0. Find the lowest energy configuration. Then you can always lower the energy by taking that configuration and flattening it out a bit. So when the gradient's not 0, that means the field is moving, is fluctuating. And this thing here is just a function of the field itself at every point in space. Not space-time, but space. And this thing doesn't care about the fluctuations whatsoever. So if there'll be points where this function is higher and points where this function is lower. And by taking the points where this function is higher and dropping them a bit, you can make the energy go down. And that will, I mean, this is not a rigorous argument. And then this can lower that quantity there, and you can repeat this process over and over again until you end up with a flat configuration. Or another way of saying it is, take this function here, take the function phi here, find where the gradient is, you find the points where the potential is minimum. So whatever configuration this will be, phi, and where will I draw it? So suppose phi is not constant, and phi looks like this. I don't know, like this. Now evaluate the potential everywhere. It's high, 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 low, 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 high, high, high. And then you just find the point which has the lowest potential. And then draw a line there, and that configuration always has a lower energy than this one here where the function is moving. It takes a couple of calculations. Right, so there's 3 constant configurations that extremize the energy, and they satisfy that equation there. So we can throw one out straight away. So the configuration phi classical equals 0, that is not a minimum energy configuration. The energy of that per unit length is 0. Seems low, right? But you can go lower. Instead, it turns out there's the other 2 solutions which occur for mu is equal to, for phi is equal to 6 mu squared over lambda square root plus minus. These actually do have a lower energy, these 2 configurations there. And I'm going to write that as plus minus v. So this potential function here that measures the energy of a constant configuration also has that double well structure. That's mainly why we put the minus sign here. Now, in contrast to the first example that we covered, this single particle in a double well, the quantum version will also exhibit spontaneous symmetry breaking. So I'm not going to do the quantum version. This is already quite a complicated calculation, the quantum version. And there the intuition is the following. So in the case of the single particle in the double well, the quantum version had a restored symmetry. The ground state was separated from the first excited state by a gap. Small gap, but a gap. Here, that's not the case. This is like an infinite number of these double wells, which sort of interact pairwise. So you think of the quantum version, if you put this on a lattice, the quantum version you can think about as a double well, a double well, a double well, a double well, and so on, blah, 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 blah. And these talk to each other. And it just so happens that the energy of these two possible minima, the one where there's the classical field is in this well, and the one where the classical field is in the other well, the quantum states corresponding to these classical configurations have the same energy, rather than being separated by a slightly different energy. And in this case, a fluctuation will quickly push the system into one or the other. So I'll say more about all these things. Actually, probably I will say some more things about this quantum side right now in the context of a lattice model. So it's a bit hard to see these features here. But there's actually a very nice lattice quantum model which exhibits all these features where you can see the quantum structure of the ground state space a bit clearer. I can almost leave this here because the quantum model I'm going to tell you about now is a lattice model called the transverse easing model. So it's very much like the classical easing model, but now it's quantum. Although I didn't say it, it's kind of clear, I hope, that that has Z2 symmetry. Just let phi go to minus phi. So far, everything's been restricted to the classical setting. I made some comments about the quantum setting, but all the examples here have been either classical Hamilton systems or statistical physics systems based on classical Hamilton systems. And I've made some general remarks of how this extends to the quantum regime. All right, now we come to our first example of a quantum symmetry breaking. This is a model pertaining to a 1D lattice of spins, quantum spins this time. And the Hamiltonian for this 1D lattice of quantum spins is this nearest neighbor term here and this magnetic field term here. the picture, I guess we could draw as something like this. There's a two-level system at every lattice site. And these spins interact according to this pairwise interaction here. If they're pointing in the x direction on the Bloch sphere, then in the same x direction in the Bloch sphere, then that has very good, that's not penalized. But if they're pointing in opposite directions in the Bloch sphere, then it is penalized. So the ground state for very small h well, there's not one unique ground state. Let's just set h equals 0. It turns out there's two ground states for this quantum model here. There's omega plus, which is just the so-called plus state, the tensor product of the plus state over all the spins. And the minus state, where those are the plus and minus states. The symmetry, this Hamiltonian has a Z2 symmetry, which is not clear. It's not absolutely trivial to see, but I'll write it out. So define this unitary operator phi is the tensor product of sigma z on all the sites. And then we have that phi commutes with h. You may have to think about this for 10 seconds, but it's phi commutes with z's by construction, and phi also commutes with this because sigma z anti-commutes with sigma x, but there's two sigma x's, so they commute as a bilinear expression in these two Pauli operators. So this Hamiltonian has a symmetry. It has this Z2 symmetry because if you do phi twice, you get 0. You get the identity again. Phi squared is the identity. And we see that for h is 0, for zero magnetic field, the system has two ground states. This one and this one. Actually, that's not quite right. The correct way to say it is that the ground eigenspace is degenerate. The ground eigenspace for this model for h is 0 is twofold degenerate. There are two possible ground states. And here is a basis for this ground eigenspace for this Hamiltonian. But in quantum mechanics, we're allowed to take superpositions of states. In quantum mechanics, there's no reason at this stage to prefer this basis to some other basis, which is a linear combination of these two states here. To actually prefer a basis would be to commit the preferred basis fallacy, or the preferred ensemble fallacy. So actually, these two states here are perfectly valid ground states for the transverse Ising model. But we never see these ground states in nature. So you can engineer materials which have these dynamics. And when you cool the system down to zero temperature, or just about zero temperature, and you set this magnetic field to 0, the system goes into its ground state. But when you do the experiment, you never see these two ground states, ever. And the reason is they're Schrödinger cat states, these two states there. So that's a massive superposition of all the spins pointing to the left on the Bloch sphere and all the spins pointing to the right on the Bloch sphere. It's a huge macroscopic superposition. And a teeniest fluctuation, teeniest amount of decoherence will immediately destroy this superposition here. So interactions with the environment will destroy these superpositions and prefer the system to enter one of these ground states. And this is a key point which explains why, even though the system doesn't actually exhibit symmetry breaking in the sense that it chooses one state or the other, it can choose any superposition as a ground state. Effectively, it does exhibit symmetry breaking because decoherence will and that's a core physical process that you have to keep in mind when we discuss more and more complicated examples of symmetry breaking at the quantum level in field theory. You must remember that decoherence is always there. There's always stray interactions with other degrees of freedom, and they will decohere the system if they're in massive superpositions like this. So decoherence will destroy the superpositions between these two macroscopically different or distinguishable states, and the system will enter a probabilistic mixture of this state and this state here. It means that the system will have exhibited a broken symmetry. So the ground states that actually you observe in the lab will be either omega plus or omega minus. The system will select one of the two. And neither of these two states is symmetric under phi. So all we know is that phi plus equals omega minus and vice versa. So the symmetry transforms you between these two ground states, but neither state has the symmetry. So that's a system with symmetry breaking. Why has it got symmetry breaking? Well, for H is extremely very large. Now turn H on to a 10 trillion, Avogadro's number, just choose the biggest number you want. Then the ground state of this system is unique, and it's the state where all the spins point up, and that is symmetric under that operation over there. Where all the spins point down, sorry. All right, so that's the quantum manifestation of spontaneous symmetry breaking. Bear in mind, it's very important that the ground state manifold of a Hamiltonian, if the Hamiltonian is symmetric under a symmetry, then the ground state manifold of the ground eigenspace is symmetric under that same symmetry. And the only reason the model selects one basis over another, the only reason the model exhibits symmetry breaking is because of this. Without decoherence, or without interactions with the environment, the ground space would not be broken, and you would any superposition whatsoever would be an equally valid ground state for the system. Okay, that's the quantum story for discrete symmetry breaking and the classical story before that. Now, I'm going to tell you about the continuous case. Oh yeah, just to amplify that point, if you were allowed to have superpositions, you wouldn't see symmetry breaking necessarily. You could find ground states that were symmetric under the symmetry transformation, namely that one there. That one's symmetric under phi. So I think I've explained now all the mechanisms for how symmetries get broken in classical and quantum systems at the discrete symmetry level. Let's talk about continuous symmetries. I've given you already a classical example of a system with a continuous symmetry, this pendulum on the table. And the pendulum on the table will choose a lowest energy configuration which breaks that continuous symmetry. And then let's study the consequences of this for field theory. I'm going to write down a field theory. It's a reasonable effective model of pions that exhibits spontaneous symmetry breaking of a continuous symmetry. So this is something known as the linear sigma model. I think we've met it either in the exercises or somewhere else before. This is a theory of n scalar fields, and the interactions are as follows. This is a set of independent Klein-Gordon equations, so it's a set of n independent Klein-Gordon scalar fields which have this quartic interaction here amongst themselves. So this notation here, I mean, perhaps it's obvious, but I should write it out, of course. That means that. Now, this is an example of a system with symmetry breaking in following exactly the same argument as we did for the Z2 case. So it turns out that dynamics if you redefine these fields as linear combinations of each other, then the whole Lagrange density and the Hamilton are invariant under orthogonal rotations, like so. For any n by n orthogonal matrix, if you redefine the fields according to this formula here, everything's invariant. So this is a continuous group of symmetries here. Now, same argument as before. We're going to look at the lowest energy configuration for this dynamical system, this classical dynamical system. Well, it's got to minimize the potential. Okay, it's going to minimize that. And we can work that out. It's an exercise for you. So the minimum occurs for any configuration, a constant configuration of these fields, which satisfies this equation here. And if you look at that equation for long enough, then you see that there's more than one field configuration which could lead to that solution there. For example, you could have that phi naught j is mu on root lambda 0, 0, blah, 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 0. That would satisfy that condition. Or this would satisfy the condition, and so on. So there's lots and lots of possibilities, and any superposition, so to speak, of those as well would do. So it's worth plotting this potential to get a feeling for those potential minima. So I can only do it in the case of n is 2. And I'll try and do my best to render this. So that's what V looks like for the case of n is 2. So I've got phi 1 and phi 2 on the x and y axes. It's the bottom of the wine bottle potential. So you know how to tell how expensive a bottle of wine is? So I don't know if anyone's taught you this algorithm. So if you want to seem really impressive at a dinner party and you want to appreciate the wine, when you pick up the bottle, you put your finger underneath the bottle, and there's this little hole in the bottom of the wine bottle. And the bigger the hole, the more expensive the wine. So, oh, this is an expensive wine. But if it's flat on the bottom, then you know it probably came from Lidl for €1.49. So this is the bottom of the wine bottle potential. This is the expensive wine, because it's got this bump in the bottom. Now, these configurations here are points at the minimum of this potential, and you can see I've drawn, I don't have any other colors today, but, oh yes I do. We'll use yellow. So the minima of the potential V, there's not just one minima, there's not just two minima, there's actually a continuous set of minimum points at the bottom of this potential. And any configuration of the fields that lies on this circle here for the n equals 2 case is a lowest energy configuration for this field theory. Easy peasy, right? Good-o. And that is not a bad analogy with the pendulum on the tabletop. The potential for the pendulum on the tabletop looks a little different, but it has the same feature that the minimum energy configurations lie on a circle. And again, as with all the symmetry breaking examples, each ground state breaks the symmetry. This is not rotation invariant, that's not rotation invariant, that's not rotation invariant. But the set, the ground state manifold of all ground states has the symmetry, and the symmetry acts non-trivially on that manifold. Now we're going to get to the topic of low energy dynamics. You know, it's all well and good that the ground state breaks the symmetry, but now we want to understand, how does the system behave for low energy? So the universe is a pretty boring place if you're in the ground state all the time, although the ground state of quantum gravity is presumably the universe. But if you're dealing with one particular field, it's a boring place to be, the ground state. There's no dynamics, nothing happens there. So we want to understand the low energy dynamics. How does this system behave when you're a little bit away from the lowest energy configuration? What are as a dynamical system, what does it look like? Now, for the Z2 case, we can, I'll just give you the physical picture of the dynamics rather than going through the derivation. We'll do the derivation in details for this continuous case here. So if you start in a double well and you're a little bit away from the potential minima, say here, then the dynamics is pretty easy to imagine, right? What happens is that it's a particle in a potential well. It doesn't really see this barrier. It doesn't have enough energy to traverse the barrier or even tunnel through it. And it just sort of oscillates like this, right? So effectively, the low energy dynamics are that of a harmonic oscillator with some corrections for a classical symmetry broken system. And they all exhibit all the classical Z2 broken symmetry systems all behave more or less like this. The dynamics of a configuration near the lowest energy one looks like that of the harmonic oscillator or the Klein-Gordon field with some corrections. And in particular, it looks like it has a mass, because this harmonic oscillator, this effective harmonic oscillator here, has some width, and that width is proportional to the mass. So it has an effective mass. There's some restoring force here to come back. So there's an effective mass to this particle, this dynamical system. Now in the continuous case, we're going to see something quite different. We're going to choose coordinates for our fields. We're going to do some coordinate changes. This is still classical. So the system breaks the symmetry. It falls into a configuration on the bottom of this circle here somewhere. And let's just choose a coordinate system by rotating so that phi naught of j equals this. 0, 0, 0, all the way down to v. And v is just this mu on root lambda. Okay, that's easy enough. And we're going to understand what are the dynamics of this linear sigma model for small fluctuations around there, for low energies. You know, not the ground state, but not high energies. Not so high that the field senses that this potential maxima there, local maxima. Instead, we're going to look at the dynamics very close to the lowest energy configurations and give an effective model for those dynamics. So the way to do this is we're going to define shifted fields. In terms of new coordinates. All right, I'm going to do this because I'm going to use a certain notation because that's the notation that people use, but I'll have to explain it because it's a bad notation. So pi here is not the momentum, conjugate momentum density. Pi is just another field. So this is the definition of our new fields, these fields here, phi, pi, and sigma, and they're defined by this equation here. This is just a way of shifting our field coordinate, the way we measure our fields. Pi comes from its application to pions. So we can rewrite our Lagrange density in terms of these new fields defined by star. And it's a lovely little exercise. I mean, you just, wherever you see a phi to the j, you substitute that vector there and into that Lagrange density up there and write it out. So I'm not going to do that, details of that, that's a good exercise. I will write out the answer though. Yeah.
How do J and K relate?
How do J and K relate is the question. Yeah, it's poor notation what I've used here. So phi j, that's meant to mean the vector phi. The j is just meant to say this is a vector. So actually, well, what I really should have done is this vector of fields is equal to this vector of fields here. So there, I think the k is pretty clear that it's just telling you what entry in this vector you're in. And that's the last entry of the vector there. Now, if you stare at this Lagrange density long enough, then you will conclude that it's a Lagrange density for a massless, for n-1 massless fields. There's no mass term for these pi's anywhere to be seen. And a massive sigma field. There's one, so I'll try and highlight that. So this term here, these two terms in the Lagrange density there, are that of an effective massive scalar field, massive Klein-Gordon field. And this pi here, these n-1 pi fields, they don't have a mass term. They don't have a corresponding mass term here. If you look through this list of all these weird terms here, they're all higher order terms, they're all interactions multiplied by lambda, right? So none of these, all of these terms here, these are small because we always think lambda is small, but they're not a mass term. Nowhere do you see anything that looks like a mass term. So this is effectively a massless n-1 massless fields and one massive field with some interactions. So this Lagrange density here, for the low energy dynamics of this theory, this is an exercise. This Lagrange density here is a theory of one massive field, n-1 massless fields, that interact weakly. And if you look back at our picture for the potential, I can explain that, the physics of these dynamics, in terms of this picture. So if you look at the potential here, at the bottom of the circle, you ask yourself, how much energy does it cost to move transverse to the circle, perpendicular to the circle? So there you have to climb up the potential in either direction. So there's a restoring force that pushes the field back. So if you want to make a fluctuation along perpendicular to the perpendicular to the circle of minima, that's going to cost energy, and that will be giving an effective mass to that direction. But if you want to walk around the circle, it costs nothing. So that's an effective massless degree of freedom. And in higher dimensions, it's harder to draw it. There's always one direction which costs energy. That's the sigma field. So sigma is a fluctuation that goes perpendicular to the circle of minima. And these n-1 guys, they all go tangentially to the manifold of minima. It turns out this is not just an accident of the linear sigma model. This is a consequence of a much more general result. Much more general result, a very famous result. Due to Jeffrey Goldstone. Known as Goldstone's theorem. Okay, in this ON linear sigma model that we've been talking about, there are n choose 2 independent continuous symmetries. That's just the dimension of the rotation group ON. And so then after this spontaneous symmetry breaking, we have n minus 1 choose 2 remaining symmetries. You know, you get, if you look at this Lagrange density there, you can see that it has still got rotation symmetry amongst the pi fields. All of these pi fields, if you rotate them, this Lagrange density is invariant under rotations of the pi fields because pi always comes with a square, square, square. So that model has lots of explicit symmetry left over in it, but some symmetry is broken. Right? So the group of symmetries of manifestly obvious symmetries of this Lagrange density, the group that does that is ON minus 1, right? The rotations amongst the pi fields. But there's no obvious symmetry between the sigma and the pi fields. So the number of broken symmetries is just the difference of this minus this. The number of obvious symmetries you had before, manifest symmetries you had before, minus the one afterwards, and you get that n minus 1 is the number of symmetries that must have been broken by this ground state. And so here's the theorem. Oh, and what I didn't, the final observation before we quote the theorem, how many massless fields are there? Well, there's n minus 1. So the number of massless fields that come out in this model is equal to the number of broken symmetries. For every broken symmetry, there's a massless excitation in this effective model. These are called Goldstone bosons. So for every broken symmetry, there is a corresponding massless boson particle, bosonic particle. And these are called Goldstone modes, Goldstone bosons. Okay, so we're going to prove this theorem in the time remaining. We can actually, this is a piece of classical field theory, what I'm going to describe here. Perfectly rigorous, everything we're going to say. So consider a theory with like fields phi A, so some bunch of boson fields. Just some tuple, and they're interacting according to whatever they interact with. And so and this theory, we're going to keep it pretty general. We're going to allow any theory that is of the form, whose Lagrangian has the form of some derivatives minus some potential of those fields. And our job is to find the potential minima, to find the classical configurations, then analyze the dynamics of fluctuations around these minima, and then somehow prove that there are n minus 1, that there, for every broken symmetry, that these classical configurations give rise to, there is a massless boson in the effective model of the low energy dynamics. So we find the classical minima, right, by minimizing the potential. Again, the argument about derivatives, that you can always smooth it out and always lower the energy, applies again. So that you can restrict yourselves to constant field configurations. And what does it mean, constant? Well, it means that you're at an extrema of the potential. So that's back to calculus. Okay, that's equation 1. That's what it means for a configuration to extremize the potential. Now, to talk about the dynamics of the system near the potential minima, we're going to approximate the potential near the minima. So for that, we need a Taylor series. And we've crucially used the fact that we're at the potential minima here in this Taylor series. So when you do a Taylor series of some multivariable function, then you have a 0th order term, that's that one there. You have a 1st order term, which is not written down here. And the reason I haven't written down the 1st order term is that it's 0 by 1, right? The 1st order term is this. So by 1, there is no 1st order term. And so the next order in a multivariable Taylor series is the 2nd order. So there it is there, and there's the Hessian, right? This is just all the 2nd order partial derivatives of the potential, like this. So that's just Taylor series for a many variable function. And we're going to give this Hessian matrix a name. We're going to call it MAB squared. Now, and I'll be a little bit more pedantic and write them like that. So this matrix M squared is symmetric and real. And its eigenvalues give the masses for the effective fields. So I didn't write that out here, so I'll just explain why that is the case. So what you do is you take the M squared matrix. Because it's a symmetric real matrix, you can always diagonalize it with an orthogonal rotation. the transpose there, I guess. So a symmetric real matrix can be diagonalized by orthogonal rotation. And then if you redefine new fields, with this O, I have the T there, so yeah, with this O, then if this matrix, then you will end up with some derivatives minus some mass terms corresponding to the eigenvalues of the D's. So when you rewrite L in terms of these pi's now, you get derivatives minus these diagonal entries here. Plus other stuff. And those are the terms that we identify as masses, yeah?
Question for the Taylor series. The second term, is it with Einstein's sum convention?
Oh yes, yeah. So the question is there a summation convention happening here in the Taylor series? Absolutely is the answer.
So the first two terms shouldn't have the A up. No, the first left from it. This one, the A there.
Yeah, if you like, yeah. So V is a function of the phi naught A's. So that's, you know, the A's are buried in whatever summation conventions we have inside the V. But if you like, it is a function just of the vector of fields. So we're using the summation convention throughout, but I'll just write the summation in there. So these eigenvalues correspond to the masses of these pi particles. So the only difficult thing we have to do now is convince ourselves that there are some massless particles, so that there are some zero eigenvalues for this matrix. So we must show that every continuous symmetry leads to a zero eigenvalue. So a general symmetry, transformation of the fields always looks like phi A goes to phi A plus some shift, which depends on the fields. So if you remember right back to the quantum field theory course last semester, Noether's theorem, we have general global symmetries which are continuous, look like this. And alpha is infinitesimal. And phi is some function. What we're going to do is going to do that transformation on the potential and see what happens. So this transformation there is a symmetry of the potential, right? Because the derivatives vanish. So that means that V of phi A equals V of phi A plus alpha delta phi A. Okay, that's pretty easy. That's what it means to be symmetric. But if you expand to first order, that implies, and equate order 1 terms, that the directional derivative of the potential in the direction of this vector here is 0. So this is an important equation. So we're going to differentiate this expression with respect to phi b. We're going to get 2 terms. So we get and we end up with that expression once we differentiate with respect to phi b for all b. There's no summation convention in place for the b, only for the a. But when phi a is equal to phi a naught, when you evaluate this expression at phi a naught, so when you evaluate this derivative at phi a equals phi a naught, then that term vanishes, right? That's what it means to be the minimum of the potential. We end up with this expression here. I'll put the summation back in. So when you evaluate this matrix here at phi a naught, you get this mass matrix M squared. But let's write this as in matrix form. This is like some vector transposed times by a matrix equals 0. It's a real symmetric matrix M squared. And we found a vector such that when you multiply the vector by the matrix, we get 0. But what does that mean? That means that's a 0 eigenvector. So for every one of these symmetries, we're going to build a vector that is a 0 eigenvector of M squared, the matrix M squared. And of course, you need to show to finally conclude that the 0 eigenspace of M squared, so this matrix M squared, we need that it has to have as many 0 eigenvalues as there are continuous symmetries, and then therefore you need to argue that this vector here, that these vectors are all linearly independent. Right? But that follows from the definition of independent continuous symmetry right back here. So if they were not linearly independent up there, then these wouldn't be independent continuous symmetries. So this is sort of how the theorem ends. The proof ends, sorry. There's another subtlety which, of course, I need to comment on, and that is there may be more, right? There may actually be more zero eigenvalues than the ones that you see here. So you can explicitly construct a continuous symmetry, and you can explicitly make them zero eigenvectors of this matrix here, and therefore they will have zero mass in the Lagrangian. But what happens, does that exhaust all of them? Well, of course, if there are additional eigenvectors with zero eigenvalues here, they lead to additional continuous symmetries. So that's how you argue that every continuous symmetry has a corresponding massless excitation. And then I think we're done. All right, so that's it for now, and I look forward to seeing you in the next lecture. Thank you.